The next thing is we'll show how the empirical formula of a compound can be determined experimentally. And one of the methods of doing that is the synthesis method. In this method, a known mass of an element, A, is allowed to react completely with another element, B, of a known mass to form a compound, C. All right? The mass of the compound formed is then measured. So you react this, you know the mass of this. You react it with this guy here, and then you form a compound C, and then you find the mass of this of C. The mass of the element B is then found by subtracting the mass of element A from the mass of the compound formed, C. If you know the mass of A, and you know the mass of the compound formed, you can know what is the mass of this guy here, because the addition of A to B gives what C is. Now that we know the masses of A and B in the compound, we can go ahead and find its empirical formula. You know the mass here, you know the mass here, you divide that by its molar mass, and then you find the empirical formula. We'll do a real example here. Let us say you wanted to know what's the empirical formula of magnesium oxide. What you do in this case, you allow magnesium to combine with oxygen, but magnesium will only combine with oxygen if it is heated in air at a high temperature. When it is heated in air at a high temperature, it forms magnesium oxide. But point to note is that when you're heating this magnesium here in this crucible here, sometimes because there's nitrogen in the air too, there will be a tendency for the magnesium to react with some of this nitrogen here to form magnesium nitride, and this can escape as a gas if the temperature is not controlled. If the temperature is controlled, you do not get the production of this, and so no magnesium is lost from the crucible. So bear that in mind. So this figure is showing you what is happening here. So here's your crucible. You weigh the crucible lid before. Then you insert your magnesium inside here. Then you allow it to react with the oxygen to form magnesium oxide here. So definitely the mass of this crucible will increase because it is accepting oxygen now. So we can know how much oxygen is being used. It didn't have any oxygen here. It's having oxygen here. So we take the mass of this guy here and subtract that mass. That will give you the mass of the oxygen there. We know the mass of the crucible and the lid, and we knew the mass of the crucible and the lid plus the magnesium. So we can subtract the mass of the crucible and its lid from the mass of the crucible and its lid plus magnesium. So this is how the calculation is being done here. So this is the mass of the empty crucible and lid. Okay. You can see when you add the magnesium before you heat it, it's this. So you can see a difference here, okay? So you can subtract this from that. Of course, that will tell you how much magnesium. It appears it is this guy here, okay? Then what do we do? Mass of the magnesium used, and that's exactly what it did there. And the mass of the oxygen used will be the final mass. That is, after you reacted the magnesium with the oxygen. So this was the mass of the crucible and its lid, and this is the mass of the crucible and its lid and the magnesium oxide. So you subtract that from that, that gives you the mass of the oxygen here. Okay, this is where it is synthesis. This is the mass of the magnesium. This is the mass of the oxygen. We can now go and see how many moles of magnesium there is in that and oxygen there. So we did problems like that before. So you divide each of these by the respective molar mass. That is for magnesium, that is for oxygen, and you end up with this here. Do not round off at this point, all right? Do not round off at this point. The point is made here that we're using 16 grams and not 32. This sometimes kids know, oh, oxygen is O2. No, you're talking about oxygen in this way and not O2. So you want full number of oxygen atoms. This is oxygen atoms, not O2, okay? So note that point there. Now you divide each by the smallest one. This is the smallest one. You divide it there. Now you can actually, because it's very, very close to 1, you can do that. The ratio here is this. Make that a subscript of the atoms here as Mg1O1. But you do not put the 1s because you assume that when you have it like this, 1 is there. So that is the formula for magnesium oxide. Secondly, you can have another way again by decomposing a compound. Now, let us say you have another compound C, and you decompose it into elements A and B. The elements A and B are then measured to calculate the empirical formula of the compound. Copper has 2 oxides, right? Copper 1 oxide and copper 2 oxide. Let us suppose that the label of a bottle containing either of these 2 oxides has fallen off. How could we go about determining which one of the oxide is present? You can go about now to find its empirical formula by decomposing this copper oxide here. And when you decompose it, you will know how much copper was there and how much oxygen was there, okay? So see how we do that now? We're not making something, we're decomposing this guy. You will get the mass of a crucible. First of all, you weigh that. Then you insert your copper oxide, we don't know which one of the 2 that is, and you weigh it again. That will help you to determine what is the mass of this guy that you put in there, like we did to magnesium. Then what do? Copper oxide, or the oxygen in copper, can be removed by heating this thing in a stream of hydrogen. See, hydrogen here reacts with oxygen to give you water. The oxygen from there will be removed by a single displacement reaction by its reaction with hydrogen here. So you'll be left with only copper, and this water evaporates, okay? So now we'll know the mass of copper there, because initially we know the mass of the crucible. So you weigh the system now, and then you can subtract and find the mass of that copper there. A known mass of the oxide placed in this crucible will then heated thoroughly in a stream of hydrogen. After the reaction is complete, you have to make sure all the oxygen has been removed from the oxide. The difference between the original and final masses of the compound will be the mass of the oxygen originally present in the oxide. See how we now do the calculation to get how much oxygen was there. This is the mass of the empty crucible. So in this case, it's 310 grams. The mass of the crucible in the oxide is 312. Obviously, now, what is it? The mass of the oxide there will be 2 grams, okay? All right, let's hold that for now. The mass of the oxygen present. So this was the mass of the crucible and oxide. But now, after you removed all the oxygen, that is what was left. So you subtract this guy from that, and that gives you 0.4 grams of oxygen. All right? You want to know the mass of the copper present. How do we get that? The mass of the copper present will be equal to this one here minus 310. What this has here is a crucible. Crucible plus copper. But this one here is an empty crucible. To find the mass of the copper load, subtract the mass of the empty crucible from the mass of the crucible plus copper, and we'll get this mass for copper, right? Now that you know the masses of each, you go ahead now and you find the number of moles of each atom present inside here by dividing the mass of each element that was in the oxide there by the respective molar mass of each element there, and you can see that is nice value there. Divide again, and end up with 1, okay? Change all these decimals to its whole number, and this is your formula there. If you had found out that this value here was 2, and that one was 1, your compound would have been Cu2O instead of CuO. Alright? I hope that was useful. Finding the molecular formulas of compounds. So empirical formula gives the smallest whole number ratio of the elements present in the compound. Now look at this hydrocarbon. This is ethene or ethylene. Ethylene has a molar mass of 28.06 grams per mole. How can its empirical formula be found? First, we find its molar mass by adding up the mass of the carbon atoms there and the mass of the hydrogen atoms there. In this case, you see that carbon is contributing 24.02 grams and hydrogen is contributing 4.04 grams. Then the percentage composition can be found as follows. You take 24.02 grams and divide it by 28.06 grams, which is the molar mass for the compound, times 100%, and you'll get that for carbon. And then you take 4.04 grams and divide it by the molar mass of the compound, which is 28.06, and then you multiply that by 100, and that will give you the percentage composition for hydrogen. So the percentage composition for carbon and hydrogen in that compound is 85.60, and hydrogen is 14.40%. Okay. So you can see now we are saying that this here is the empirical formula for this compound. But watch this table here. These are a series of hydrocarbons called alkene. They all have the same empirical formula, and because of that, they will have the same percentage composition by mass. So if someone were to give you the percentage composition of a hydrocarbon, and they give you these values here, you can use these values here to find its empirical formula, because we've done that before. What we said, how do you find the change these to grams? You'll take 85.6 grams, 6 grams, and you take 14.4 grams, and you divide each by its specific molar mass, 12.01, and that one 1.01, and you end up in the end with this empirical formula. Let's see it on there. That's just to check your memory there. Okay, what is it? Now they're showing you here what you do. So you have that percentage composition there. What will be its empirical formula? Let's say you didn't know what is its empirical formula, but they say, you know what? A compound has these percentage compositions by mass, right? How do you know its empirical formula? Okay. You do the same thing as alluded to just now. You take these here and you divide them by their respective molar mass for its element. Okay, this one here for hydrogen, that's this one carbon, the hydrogen, and you end up with this. You have decimals here, you divide by the smallest one. This is the smallest one. It is 1 to 2, and this here is the empirical formula. But watch. It doesn't tell you which compound you're talking about. Every one of these here has the same empirical formula. So how would we know which formula we are talking about this compound? They will have to give you some additional information. So they'll give you the percentage composition. You will find its empirical formula to be this, but this can be attributed to any one of these. So they need to give you an additional information so that you can calculate which one of these is in question. Okay, so the additional information is the compound is having a molar mass of this, 56.12 grams per mole. The next thing we want to know is how many times the molar mass of the compound is as heavy as the molar mass of its empirical formula. If you remember the very, very beginning of the lesson, I showed you how C2, you have C2H2, right? C2H4, and this guy was able to go 2 times into that. So we want to see how many times now this guy can fit into that. So we know how many times this one here is heavier than this one here. So what we'll do, we'll find the molar mass of this empirical formula here. You have 1 carbon, every 1 mole, there. You have 2 moles of hydrogen, and that will be there. So its molar mass will be found by adding up those 2. So the molar mass of this guy here is this. Now we want to see how many times this mass here for the real compound is as heavy as the molar mass for the empirical formula. So what do we do? We take that molar mass for the real compound that you want to find, and divide it by the empirical formula mass, okay, and you get a multiple of 4. So whatever that compound is 4 times as heavy as its empirical formula mass. So how you get that? You take this multiple that you have here, right, and you multiply the subscript of each element by 4. You know it is carbon is 1, multiplied by 4. Hydrogen was 2, multiplied by 4. So you end up with C4H8. This is the formula that you're talking about of the compound. You want to check it out? See if this weighs, see if that when it weigh exactly what you're given. You have 4 moles of carbon, that means molar mass, it's just this. Alright? You have 8 moles of hydrogen, which is this. When you add all these up, you end up in this. So quick review. Here you're seeing, from this table here, a number of compounds are having the same empirical formula. And because of that, they'll have the same percentage composition. So if you're given the percentage composition, they will tell you, look, the percentage composition of a hydrocarbon is 85.60 carbon and 14.40 hydrogen. We want you to ascertain the molecular formula of the compound, but they will give you what is the molar mass of the compound. So what do? Use these here to find the empirical formula of the compound. Change it to grams, change percentage to grams, mass in grams. Then you find the number of atoms for each. Doing that, we did the empirical formula already, and you found that it is this, 1-to-1. So the empirical formula is this. We didn't know about the empirical formula, you just given percentage composition and the molar mass of the compound, right? Next thing you do is to find the molar mass of the empirical formula. So it has 1 carbon, and that's equal to 10.01, 2 hydrogen, this, add these 2 together, and you get 14.13 grams per mole. This is what is it for its empirical formula. Now that they have given you the molar mass of the compound, they have given you the molar mass of the compound, which is this, all right? You take that and divide it by the empirical formula
mass
to see how many times that compound there is as heavy as its empirical formula. It'll give you a multiple here. You take that multiple and then multiply each of the subscript here by it, and that will give you its molecular formula. And this is what it is in this case. So to know that you're correct, find the molar mass from this here and to see whether or not it corresponds to the one that was given, and this is what it is. So I hope that was useful. So some nice, beautiful questions here. All right, some nice practice problems here. On each one of these, a compound, you can learn about the functions of these compounds too. All right. Note also at the end of every chapter I've not shown here, you have lots of multiple choice questions and true and false matching questions and so on, but they're repeated in the everything, every exercise, every set of multiple choice and everything are repeated in the solutions manual, and the solutions for those are also good. But I hope that was useful.